finally, let's take a look at one more example. Here we have a graph that is falling and doesn't go through the origin, but crosses the y-axis. So that tells me that it's an exponential function where our base is less than 1. We have a decreasing exponential function. On what interval or intervals is the function increasing or decreasing? Well, this graph is decreasing across its domain, which is all real numbers. In which way is the graph concave? This graph is concave up. Something in the real world that a function of this shape could model, well, something that decreases exponentially, which could be any isotope, radioactive isotope, which has a half-life. Now, to find the particular equation, once again, we're going to take the same approach we took with the last three examples. We're going to start with the general equation for an exponential function. So y equals ab to the x. And we're going to plug in our values for x and y and solve for our unknowns. So our first equation would be when y equals 10, x equals 2, so ab squared. When y equals 6, x equals 5, so ab to the 5th. Now I'm going to use the same process I used in the last example. I'm going to eliminate the unknown a by dividing one equation by the other. But I'm going to divide the 6 equals ab to the 5th by the 10 equals ab squared, because when I do that, since through the process of division, I subtract exponents, so that gives me 0.6 is equal to, with my a's canceling out, b to the 5 minus 2, or b cubed. To solve for b, I need to take the cube root of both sides. So b is going to be the cube root of 0.6. If I pull out my calculator here, I will take 0.6 and raise it to the 1/3 power, which is the same as taking the cube root, and find out that my b value is going to be 0.8434. Now that I know my b value, I can go back and solve for a using either of my equations. So I'll use the first one here, and I will say that 10 equals a times 0.8434 squared. So a is equal to 10 over 0.8434 squared. Which again, if we pull out our calculator, becomes 10 divided by 0.8434 squared, or approximately 14.0583. Which, when placed into our equation, becomes 14.0583 times 0.8434 to the x. Let's recap. What are the visual characteristics that allow us to determine the type of function from a graph? Well, we look at whether a graph is increasing or decreasing, and the concavity, and in particular whether it goes through the origin to distinguish between power and exponential functions. A linear graph is strictly increasing or strictly decreasing. If it hasn't been transformed, it goes through the origin. A quadratic function will either decrease then increase, or increase then decrease. And if it hasn't been transformed, is again attached to the origin. A power function has three possibilities. If our power is greater than 1, it will be increasing go through the origin and be concave up. If our power is between 0 and 1, it will be increasing, go through the origin, and concave down. If our power is negative, we will have asymptotes along both the x and y axes. The graph will be decreasing and concave up. What information from a graph is necessary to solve for a function's equation? Well, we need points on the graph. For a linear graph, since the general equation has two unknowns, a and b, we need at least 2 points. For a quadratic function, we have 3 unknowns in our general equation, so we need at least 3 points to set up a system of equations. For the power function, here our general equation has 2 unknowns, so we should be able to solve with just 2 points on the power function. The exponential function also has 2 unknowns, so we should be able to solve with 2 points. How do we solve for the equation given a graphical image? Well, in each case, we're going to use the same technique to start with. We'll take the information from the equation, or from the graph, the points on the graph, and place them into our general equation, creating a system of equations with unknowns. Then we solve that system either through elimination or substitution. In the case of the quadratic form equation, when we have a system of 3 equations with 3 unknowns, using matrices is probably the most efficient way to determine our 3 unknowns a, b, and c. When we have a power function, we use division for elimination, and then we, hopefully by inspection at this point, can solve for our power and subsequently solve for our coefficient. For our exponential function, again, we take our system of equations and use division to eliminate a variable. When we have our unknown raised to a power, we can reduce to the first power by taking the reciprocal of our power. So b cubed gets reduced to b by taking the third root of both sides. And finally, some real-world examples discussed in this section. Well, for a linear function, anything we do on a regular basis, increasing our bank account by a regular deposit or decreasing our bank account by a regular donation. Quadratic function, something that rises then falls, anything that we throw, a projectile. Power functions, the distance it takes to stop as a function of our velocity, or how much our volume changes as we increase a dimension. The exponential function could be model a exponential decay situation with a radioactive isotope.